Hey guys, it's Dr. McJunkin back for week 3 of virtual learning. Let's go ahead and get right down into it. For lesson 5, we're going to be talking about independent events and complements of events. This is the last part of textbook chapter 9.7 before we move on next time. So, like it says at the top, we're going to be looking at independent events. What are those? And find the probability of complements of events. So first off, let's have a definition. So two events A and B are independent. So two events A and B are independent when the occurrence of one has no effect on the occurrence of the other. For example, if I flip a coin, that does not affect the result of a subsequent die roll. So if I flip a coin and get heads, doesn't make a 3 or a 4 on the die any more likely. They're very different, distinct things, so they have no influence on each other. So if we have independent events, we have a very simple probability to find the probability that both events occur. So if I want A and B to occur, and A and B are independent, such as like a die and a coin, then all we have to do is use this formula where we multiply the probability of the first one happening times the probability of the second one happening, as long as these are independent events. So this only works if these events are independent. Some events are not independent. That's what we'll talk about on Friday. This can be extended to any number of independent events, so not just two. So if I wanted A and B and C and D to happen, as long as they were all independent, I just multiply the probabilities together. So let's see how simple these can be. So for this example, we have a random number generator, so it can generate any number randomly from 1 to 20. And I want to find the probability that all three numbers, so I want to look at three different integers, all three are less than or equal to 5. So less than or equal to 5 is what we're looking at here. So what's the probability that I get a number that's less than or equal to 5? Well, there's the number 1, 2, 3, 4, and 5 that are less than or equal to 5. So there's 5 of them. There's 20 total options, 1 through 20. So there's 20 total options. If I reduce this fraction, there's a 1/4 probability that I get a number that is less than or equal to 5. So if I want to get the probability that we have a number that's less than or equal to 5, and we have a second number that is less than or equal to 5, and we have a third number that is less than or equal to 5, these are all independent events. Randomly drawing a 2 on the first one doesn't affect the next randomly selected integer, so I'm going to multiply these probabilities together. So I get the probability of the first one being less than or equal to 5 times the probability of the second one being less than or equal to 5 times the probability of the third one being less than or equal to 5. And that just becomes 1 over 64. I like to keep things in fractions. You know me. So the probability that three numbers are less than or equal to 5, if I'm choosing from 1 through 20, is 1 in 64. Not a huge probability. Okay, let's see another easy example, I think. So another probability of independent events. In 2015, approximately 65% of Americans expected that much of the workforce would be automated within 50 years. In the survey, we're going to select 10 people randomly, and we want to find the probability that all 10 people expected that the workforce was going to be automated within 50 years. Well, so the probability of my event A, where A is going to be the probability or the event thinking that the workforce will be automated within 50 years, that's 65%. And I'm going to go ahead and put this as a decimal. I know, Dr. McJunkin, you always use fractions. Why are you using decimals now? Why not? So the probability that people think that is going to be automated within 50 years, that any given person thinks this, is 65%, or 0.65. If I wanted 10 people to think this, that is 10 independently different people. One person's opinion doesn't affect another person's opinion. These are random people that probably don't even know each other. So for 10 people, I take that probability, which is 0.65, and there are 10 people. So I would multiply this 10 times. But I don't want to write that down. That seems like a lot of work. So I'm going to put this to the 10th power. It's 0.65 times 0.65 times 0.65, etc. 10 times, because I have 10 different people, and each individual probability is 0.65. So if I approximate that, then I get about 0.013. That is a 1.3% chance, very small percentage, that 10 random people think that this is going to happen. Even though the initial probability is pretty high, 65%, the probability that I find 10 people, all 10 people say, yes, I expect that, is a pretty low probability. Okay, these are pretty simple examples. Let's do one more before we move on to complements. You roll a die, so we're going to roll a die, and we're going to toss a coin. What's the probability of rolling a 4 on the die and the coin landing on tails? Okay, dice and coins, they are independent events, so they don't really matter to each other. Even like multiple rolls of a die or multiple tosses of a coin, doesn't matter if I get heads and heads and heads and heads, the probability of the next coin toss is still 50-50 heads versus tails. So all this stuff is independent. So I want to figure out what's the probability of rolling a 4. What's the probability of rolling a 4? And I also want the probability of the coin landing on tails. I need both these probabilities, and then I'm going to multiply them together because they're independent. Well, if I want to roll a 4, there are 6 total sides of the die, so that's the total number, but there's only one 4 on that die. So the probability of rolling a 4 is just 1 out of 6. The other 5 out of 6 times we get 1, 2, 3, 5, or 6. Probably getting tails, well, that's always 1/2. Probability of heads, probability of tails on a coin, always 1/2. So if I want to find the probability of a 4 and tails, well, that's easy. I just take the probabilities, 1 out of 6, 1 out of 2, and so my probability here is 1 out of 12. Easy. I just take probabilities and multiply. This should not be that hard. Okay, moving on to complements. So, the complement, not like, oh, you look so nice today, but the complement, with an E, not an I, the complement of an event A is the collection of all outcomes in the sample space that are not in A. So the complement of an event is denoted by A prime, this little apostrophe here. A prime, A apostrophe, I call it A prime. So if I want to find the probability of the complement, say the probability that something is not going to happen, all I have to do is just subtract from 1, if it's a decimal. Or if you want to think about it as like 100% minus the probability or the percentage of A, you could do it as well. I like to work with decimals or fractions though, generally, so I usually subtract from 1 and use this probability. This should be common sense. So for example, if the probability of winning a game is 1 out of 4, like you have a 1 out of 4 chance of winning, well, the probability of losing, which is not winning, is 3/4. Everything has to add up to 1 or 100%. So if it's not me winning, it's me losing. There's no ties in this game, apparently. So if the probability of winning, I guess, if the probability of winning is 1/4, the probability of not winning, which includes ties, because you didn't win if it's a tie, the probability of not winning is 3/4. You didn't win. Okay, so let's do one easy example and then one trickier example. Then we'll be done. The probability that math class will be boring is 0.72, 72%. Oh, that's probably true. What is the probability that math class will finally be fun for once? Oh, let's figure that out. So the probability that it is boring, probably is boring is 0.72. So if I want to find the probability of boring prime, which is not boring, or fun, well, that's 1 minus 0.72, and that's 0.28, a 28% chance that this math class will actually be fun for once. Not a high percentage. How sad. Okay. Now, how can we use this complement stuff, which was super, super easy, to do something a little more challenging? A manufacturer has determined that a machine averages one faulty unit for every 1,000 it produces. What is the probability that an order of 200 different units will have one or more faulty units? Okay, so what's the probability that I have one or more faulty units? If I didn't have the ability to do complements, what I'd have to do is add up the probability that one was faulty, plus the probability that two were faulty, plus the probability that three were faulty, all the way up to the probability that all of them were faulty. That's a lot of adding, which I don't want to do. I don't want to add up all those probabilities of one being faulty, two being faulty, three, etc. So what I'm going to do is complements. If I have the probability that one or more is faulty, that's the same as 1 minus the probability that all are great, not faulty. Let's say all work fine. So if I can find the probability that all of them work fine, the complement of that is that at least one of them doesn't work fine. So I just subtract from 1. So how do I find the probability that every single one of them is fine? Well, these are all independent events again. It kind of is going to look like the survey example with the 10 people. The probability that one is fine is 999 over 1,000. Well, why is that? There's 1,000 different, there's 1,000 units they're producing here. And for every 1,000, there's one faulty one. So there are 999 good ones. So the probability that I find a good one, is 999 over 1,000. Pretty high probability. Probability that all 200 are fine. Well, I need to take that probability that one is fine, 999 over 1,000, and raise it to the 200th power, because there's 200 different units in this order. Okay, so the probability that all 200 are fine, approximation bars, is about 0.819. And I always round to 3 decimals when I'm doing it this way. So round to 3 decimals here so you can be accurate. So the probability that all 200 are fine is 0.819. That's what we just found here. The probability that all work fine, all 99 are fine. So that is then 1 minus 0.819, and that means that there's a 0.181 chance that at least one is faulty. At least one faulty. Again, realize the power that we did here. We didn't have to add up the probability that 1 was faulty plus 2 was faulty plus 3. That would take forever. We instead found the complement of everything being perfect. So this technique works really, really well when you have this wording like the probability that at least one or more faulty units, or at least 2 or more. You can just subtract off the probability that all work fine or that all but one work fine. You can just subtract those off instead of having to add up 200 different probabilities. Okay, so this example is definitely the trickiest. So I'll star that one. I would definitely rewatch this example and come to office hours if you have any questions about this example specifically. The other one should have been fairly straightforward, so your classwork should also be fairly straightforward today. If you've got any questions, again, feel free to email me between 9:30 and 11:30, and I'll be in office hours from 2:45 to 3:45. Have a great day, guys. I will see you on Friday.